Good morning. Today we're going to talk about Ohm's law and DC power. We're also going to look at some simple LED circuitry. Ohm's law. Electromotive force or pressure measured in volts is equal to the intensity of electron flow or volume measured in amps times the resistance to that flow measured in ohms. V equals I times R reads as voltage equals amperage times resistance. The I in the equation stands for the German word for intensity. Fluid dynamics also operate under the principles of Ohm's law and provide an analogy for understanding. So voltage on a wire is equivalent to the water pressure in a pipe. So if you looked at a piece of wire, examined a wire with insulation, and saw on that wire, printed on that insulation, 600 volts, you know that that wire's insulation is capable of handling 600 volts of electrostatic pressure. Past 600 or over 600 volts, the insulation could break down and you could arc to ground. The equivalence would be water pressure in a pipe. If you look at a piece of plastic pipe, PVC, you'll see that it will have a pressure rating on it. So a piece of 300-pound pipe will take a water pressure up to 300 psi. Above 300 psi, the pipe has a good chance of breaking and water leaking out. So it's a direct equivalence. The water pressure breaking open a pipe or voltage, high voltage or electrostatic pressure breaking down the insulation on a piece of wire. Then it follows through even more that amperage or current flow through a wire is equivalent to the volume of water flowing through a pipe. So if you imagined a pipe with 40 pounds of water pressure, like a pipe in your house, has 40 pounds of city water pressure on it, and no water is flowing, all the taps are closed, and that would be a static water pressure of 40 pounds. And no work is being done because no water is flowing. And so you could have a battery that you could measure the potential of that battery or two wires connected to a battery, right? You could measure the potential of those wires and you could see that it would be 12 volts, right? So it's that much pressure, but nothing is happening because there's no current flowing. The wires aren't connected and current can't flow. This is just like in a pipe when the valves are closed, no current can flow. So in an electrical circuit, if we connected the wires and allowed the current to flow through the circuit, then the resistance, any resistance in that wire, the resistance of that electron flow is equivalent to a restriction in the movement of water through a pipe. So back to our house example, if we have 40 pounds of pressure in our pipe and we open up the tap a little bit and we measure the flow of water coming out, and we have like 1 glass of water per minute, right? A little flow. And if we open that tap a little bit more, we get a little less restriction. We get more water flowing. We might get 2, 3 glasses of water a minute, open it up more and more. We still maintaining our 40 pounds of pressure in our pipe. As we open up the tap more and more, we reduce the resistance to the water flowing. We get more and more water flowing out of our pipe. And resistance to electron flow in a wire is the same way. It works just the same way. So if you have a resistor in your wire, then it's a high resistance. It restricts the flow of electrons greatly, and so you have a small amount of current. And the lower the resistance, the greater amount of current could flow under any given pressure. So if we look uh, at my Ohm's law mnemonic, we'll see it's mine. This is what the victor comes out on top. Victory, V equals victory. That's the way I think of it. I mean, the victor always comes out on top. So if you look at the little pyramid, you'll see that V is over I and R. And the equation is V is equal to I times R. Then if we looked at, for instance, if we looked at I, so I is equal to V over R. I is equal to V over R. If we look at R, we see that R is equal to V over I. So this little triangle with the victor on top is a simple mnemonic to remember the construction of Ohm's law. That's the one I use. So now let's look at the simplest circuit that we can achieve, about the simplest circuit we can achieve, and that's going to be a power supply and a resistor, a very simple circuit. So if you have a power supply of 5 volts and you want to set a limit on the current flowing through the circuit to 100 milliamps, that is 1/10 of an amp, what size resistor would be required? So Ohm's law is V equals I times R. And we know that we have 5 volts, and we know that we have 100 milliamps, or 1/10 of an amp, and it's multiplied times R. So if we solve for R, we find R, looking back at our mnemonic, is R is equal to V over I, and so 5 divided by 1/10 of an amp is 50 ohms. So the resistance that is required to limit current to 100 milliamps with a supply voltage of 5 volts is 50 ohms. So now we know we have a 50 ohm resistor limiting current to 100 milliamps on our 5 volt circuit. So how much power does the resistor have to dissipate? So the power equation is derived from Ohm's law, and power in watts is equal to voltage times amperage. That is, P is equal to V times I. So if we have a voltage of 5, and we multiply that times our amperage of 1/10 amp, our power is equal to a half a watt. Our simple circuit then would need a half watt 50 ohm resistor to place in series with our 5-volt power supply to achieve a current of 100 milliamps. So now let's look at simple LED circuits. Okay, light emitting diode acts almost like a short circuit if placed directly in series with a power supply. This effective short circuit will damage the LED and could damage the power supply. LEDs have a forward voltage drop. The forward voltage drop is the level of voltage at which the diode switches on, typically 2 to 4 volts. LEDs also have a forward current limit, which if exceeded will damage the diode. These currents vary greatly depending on the brightness or power emitted by the LED. Forward voltage and current specifications must be found on the specific LED datasheet. You can't begin to engineer your circuit until you know the values or the specifications of your components. Now, an LED needs a resistor to limit the current flow through it. The GPIO on the Raspberry Pi supplies 3.3 volts to the traffic light diodes. The GPIO can only safely source about 3 milliamps. That's 3/1000ths of an amp per pin. So what size resistor will limit the current to 3 milliamps for an LED with a 2.1 volt forward voltage drop on a 3.3 volt power supply? So if we take our 3.3 volt power supply and from that we subtract the 2.21 LED forward voltage drop, that leaves us with a 1.2 volt to drop across the resistor. That's Kirchhoff's law. You don't have to know that. But the sum of the voltage drops in a series circuit is equal to the supply of the circuit. That's Kirchhoff's law. So we have 1.2 volts that we need to drop across the resistor. So if we look for a resistance where 1.2 volts divided by 3/1000ths of an amp, we find it's 400 ohms. And the power that would be consumed or dissipated by that resistor would be 1.2 volts times 3 milliamps, or it would be 4/1000ths of a watt, or 4 milliwatts. So the next thing I did is I measured a live Raspberry Pi traffic. I measured live Raspberry Pi traffic, and I found that across the red LED, I had a forward drop of 1.88 volts. And the GPIO pin, when that red LED was turned on and loading the circuit, was 3.16 volts. Now, I flagged that because that is significantly lower than what I would expect at 3.3 volts. Now, I measured the voltage drop across the resistor, and that voltage drop was 1.28 volts. If we look at the forward drop of the red LED and the voltage drop across the resistor, we find that, lo and behold, they add up to 3.13 volts. Kirchhoff's law. You don't have to know that. Now, the measured resistance of the resistor on the RPI traffic light was 330 ohms. So if we work our Ohm's law, uh, solving for current, we get 1.28 volts divided by 330 ohms gives us a current of 4 milliamps. I also measured the GPIO pin without the LED loading it down. And open circuit, the voltage on that same GPIO pin, header pin, measured 3.29 volts. So I reached a conclusion from taking these measurements. The low voltage lab traffic Pi LED overloads the Raspberry Pi GPIO. So, but by how much? Well, we could say, well, safely 2 to 3 amps, or 2 to 3 milliamps. That's what the book says. But we could figure out exactly how much power we're dissipating in the junction that pulls down that GPIO pin and lights the LED. So we take the 3.29 open circuit voltage and we subtract that from that the 3.16 volts loaded of the circuit loaded, and we get 1.3 volts. Now, or excuse me, 0.13 volts. Power is equal to voltage times amperage. So 1.3 volts times 4 milliamps gives us a power of a half a milliwatt. So we are smoking our Raspberry Pi at a level of 0.5 milliwatts. That's how much power we're dissipating in the junction that pulls down that pin. And how long the Raspberry Pi could operate under that overload condition, I don't know. However, I wouldn't operate the Raspberry Pi under that loading condition for very long. So, the next thing I'm going to move to is the actual lab demonstration. I'm going to show you the taking the actual measurements so that you can see that this stuff works. It's science.